Okay, here we are. This is going to be our last lecture for the semester. This is section 6.4, and we're going to do part 3. We're going to talk a little bit more about independence. And this represents, I think these are examples 5 and 6 in the book. I've got them labeled 5 and 6. And I know there's some examples afterwards. I think this will take care of what you need, so don't feel like you need to read the others. And I say that not that I don't want you to see the other stuff and learn from the other stuff, but sometimes I think, especially probability, it's real easy to get in too deep, and the more you start reading about it, or the more it's thrown at you, the more confused you get. So I'm going to try to make this simple and we'll get through it. To do these problems, if you go back and look at this page here, this is the previous page that I did in the other lesson, there was 2 formulas, conditional probability. And if you want to know whether 2 events are independent of each other, then if you find these numbers here, for example, the probability of E given F, and the probability of F, and the probability E and F, if you find those probabilities, then if you plug those numbers in, then you can find out if they're true or not. So if they work, basically, yes, they're independent. If they don't work, then they're not. So I'm going to use those 2 formulas. On example 5, I'm going to use the first formula, which is this one right here. And I know I get messy, so I tried something a little different this time. So I have already got some of this taken care of. So the problem, just to read it real quick, it says an experiment consists of observing the outcome of 2 consecutive rolls of a die. Let E represents the first roll as a 3, and F says the second roll is a 6. Okay, so we're going to use this formula here. We'll use this for both A and B on number 5. So I got the probability of E given F equals the probability E and F over the probability of F. Okay, so that means F, since F had the second roll of a die being a 6, I could have 1 and 6, 2 and 6, 3 and 6, 4 and 6, 5 and 6, 6 and 6. That's what F would be. Every one of those has a 6 coming with the second roll. So the probability of E given F, E says the first roll was a 3, so out of these 6, which one had a 3 come first? Well, it's this guy right here. So that was 1 out of those 6, so that's the probability of E given F. Okay? What's the probability of E and F? Okay, I'm going to go back to this page real quick. So that means we got a 3 on the first one and a 6 on the second one. That gives us this sum of 9. That means we've only got 1 out of 36. So that 1 out of 36, that's where that probability comes from. Okay, and then the probability of F, well, that was any of these 6 out of the 36, so that's 1/6. Okay, so what are we going to do? We're going to plug that into the formula. Okay, plug in, that's what that says. You can't read it real well. So the probability of F was 1/6. I put that here. The probability of E and F goes on top, so that's 1 over 36. So this one came here, that one came there, and this is the bottom one. That's the probability of F. So all we got to do is take the second part and simplify that. And by the way, I usually put a question mark on top of that because we're asking, is that true? Okay, so looking at the right, that's 1 over 36 divided by 1/6, or that's 1 over 36 times 6 over 1, which is 6 over 36, which is 1/6. So we got 1/6 equals 1/6, and that's true. So what that tells you is E is independent of F. So yes, they are independent. Okay, that's 5A. Let's look at 5B. 5B, E is, okay, we got two cards. We're going to draw two consecutive cards. That means we're not putting it back. So E says the second card is black, and F says the first one is red. Okay, so what's that one going to look like? So again, we're going to use the same formula. The probability of E given F equals the probability of E and F divided by the probability of F. All we have to do is find each of those. Okay, so E says the second card is black, so I'm just going to say, okay, and F's the first card is red. I just copied those from my sheet over there. So the probability of E given F. Okay, let's talk about this a second. So we're given F. That means we're given that the second card is going to be black. Okay, so if we already had that card out, we're taking a black one out. First of all, how many cards are left in the deck? Well, there's only 51 because I took one away. I was given the first one as a black, so that one black card's gone, that leaves 51. How many red cards are still in there? All 26. So there's 26 red out of 51 total. So that's the probability of E given F. Okay. What's the probability of F? F was the second, or the first card was red. The first card was red. Well, when you're going for the first card, there's 52 cards altogether and 26 on red. That's half of them. Okay, and then the last thing, we got to find the probability of E and F. Okay, so the probability of E and F, think of it this way. Come off to the side here. The probability of getting a red card on the first card, there's 26 red out of 52 total. Okay. What's the probability of a black one on the second card? Okay, now this has nothing to do with what came first or anything, but that's 26 out of 52 also. So that's what I have down here, 26 over 52 times 26 over 52. I put this up here because I was going to show you the blanks. We did that back in chapter 5. So it's 1/2 times 1/2, which is 1/4. Then you plug your numbers in. So the probability of E given F, that's 26 over 51. The probability of E and F, that's what I calculated here, so there's 1/4. And the probability the first card is red is 1/2. So if we simplify this one, that's 1/4 divided by 1/2. That's 1/4 times 2 over 1, which is 1/2. So is 26 over 51, is that equal to 1/2? And the answer is no. So that means they are not independent.